You know, offshore wind is one of our biggest shots at getting massive amounts of clean energy. I mean, these things are colossal. They stand out there in the sea like giants, and they have the potential to power millions of our homes. But actually harnessing that raw, wild power, well, that's a huge engineering challenge. So let's dive in and see what it really takes to tame the wind.
I mean, just look inside one of these machines. It's not just a big pinwheel. It's an incredible symphony of complex parts. We're talking gearboxes, generators, massive shafts, and blades that are over 100 meters long. For all of this to work together safely and efficiently, you need some unbelievably sophisticated control systems running every single second of every day.
And that really gets us to the heart of the problem. The wind is, well, it's wild, it's gusty, it's chaotic, it's totally unpredictable. But our electrical grid, the thing that powers our lives, it demands the complete opposite. It needs Swiss watch precision, a perfectly stable, unwavering supply of power. So how in the world do you connect those two? How do you turn that chaos into perfect, predictable order?
Well, the answer is all about solving a fundamental challenge for the grid. It's this constant, delicate balancing act. And that's exactly what researchers from the University of Tabriz and Adelberg University have tackled head-on. Their work is what we're going to break down today.
Okay, so the one critical vital sign we really have to watch here is something called AC bus voltage. This is basically the main electrical hub inside the turbine. The easiest way to think about it is as the system's electrical pressure. If that pressure wavers, the whole system starts to become unstable and unreliable.
Let's try an analogy to make this crystal clear. Just imagine our entire electrical grid is like the water system for a huge city. In that system, the AC bus voltage is like the water pressure in the main pipes. Right? If the pressure is too low, you just get a weak little trickle from your faucet. But if it's too high, boom, the pipes could burst. It has to be kept in this very narrow, perfect range all the time, even when millions of people are turning their taps on and off. That's the incredible level of control we need for our power grid.
Now, of course, engineers have had control methods for years. But as this table from the research points out, they've got some serious drawbacks. A lot of them are super complex to set up, they need a ton of computing power to run, and they really struggle with the unpredictable, nonlinear nature of wind. So you can see why there's a real need for a smarter, more adaptive solution.
And that is where our solution comes in. So let me introduce you to the DeepFWX controller. It's a brand new AI-driven system designed specifically to master this balancing act for these giant offshore wind turbines.
Now, the really cool thing about DeepFWX is that it's not just some one-trick pony. It's a hybrid system, and it brilliantly combines three powerful ideas from control theory and AI into one super smart system. The name itself, DeepFWX, kind of gives it away. It stands for Deep Fractional-Order Wind Turbine Expert Control System. Let's break that down.
It's basically a three-part superpower. And it goes like this. First, it uses something called fractional order calculus to model the system with incredible precision. Second, it uses model predictive control to actively predict the future. And third, it uses a random forest AI to make expert estimations. Let's take a quick look at each one.
So first up, precise modeling. Think about the difference between a piano and a sound engineer's mixing board. A piano can only hit distinct, separate notes. But that mixing board, it's got dials you can turn smoothly and infinitely. That's what fractional order modeling does. It allows the controller to understand the turbine's dynamics with way more nuance and precision.
All right, part two, predicting the future. This is where it gets really smart. A great quarterback doesn't throw the ball to where the receiver is, he throws it to where the receiver is going to be. This controller does the exact same thing. It's constantly running simulations to predict what the turbine's going to do in the next few moments, so it can make adjustments proactively, not reactively.
And the third superpower, the AI brain of the operation, is called a random forest. The best way to think about this is like having a whole team of medical specialists. Instead of just getting one opinion, you have hundreds of decision trees that all look at the data and then vote on the right diagnosis. This team approach makes the final call incredibly accurate and reliable.
Okay, so the theory sounds incredible, right? You've got this super precise model, a brain that sees the future, and a whole team of AI experts. But does it actually work? Let's get to the results.
And in this graph right here, this is the proof in the pudding. The dashed red line, that's the target AC bus voltage. That's perfection. The solid blue line, that's the DeepFWX controller in action. As you can just see with your own eyes, it tracks that target with absolutely stunning precision.
Just how precise are we talking? Well, the researchers used a metric called R². On this scale, a score of 1.0 is absolute perfection. The DeepFWX system scored a 0.99. I mean, that is just ridiculously close to perfect control.
And it wasn't just that one metric. Check out this table. The mean absolute error, basically the average mistake it made, was super low. The root mean squared error, which really penalizes big mistakes, was also minimized. Across the board, DeepFWX just knocked it out of the park.
Okay, so the numbers are fantastic. But what does this actually mean for us, for the real world? This is way more than just a cool piece of engineering. Let's zoom out for a second and look at the big picture for our energy future.
Look, here's why this is such a huge deal. A controller this smart and stable is an absolute game changer. It means we can integrate more unpredictable renewables like wind and solar into our grid without making it shaky. It makes the entire grid more reliable, more resilient, more efficient, and it really paves the way for a truly intelligent, adaptive energy grid for the future.
And that really leaves us with this one big, exciting question. This technology gives one single wind turbine the power to think ahead. So what becomes possible when our entire energy grid can do that? What happens when every part of the system can anticipate our needs and react before we even know there's a problem? That's the kind of future this research is helping to build.